Hi, everyone. So this is just to say a quick word. I'm about to say exactly what I said yesterday, and I'll say it again around 10 o'clock. So please try to sign up for the launch discussions that we have online. So if you go online on the schedule, you'll see the launch part. If you click it, there are sign-up sheets for launch discussions. So what do we mean by launch discussions is just people trying to get people to go together and eat together and talk about some topic. I think part of the whole thing of the workshop is for people to get to have just off-the-cuff discussions about various topics relevant to the workshop. So I'm really hoping people do sign up. Around 11 o'clock or so, we'll decide, we'll put up on the discussion, on the sign up sheet, we'll put up the restaurants where people can go. It's not super well organized. We'll find a way to get people to the restaurant they need to get to. So, but if you have questions, please ask me anytime. And then Veitch want to tell you.
Yeah. So, and then at the close of the workshop tomorrow in the afternoon, at the last event for the workshop, we're going to have a panel. I'm hosting a panel, star-studded panel, including Shai here, and a few other people who are all actually, turns out the speakers tomorrow are all going to be on the panel, and I'll come up with some questions that hopefully will spark some discussions and some disagreements, friendly disagreements. Yeah, please stick around tomorrow and think about questions you might have for the panel.
Okay, so the first speaker today is Victor, and he's going to tell about alignment in LLMs, which we all are curious about.
Okay, yeah, so thank you all for getting up early and coming to the first session. This is a new talk, and so if it's confusing, please interrupt me. Okay, so I'm going to be talking optimistically about two papers from my lab. One, oh, do I have a laser pointer? I guess not. Okay, well, one, the bulk of the talk is going to be about this paper, BonBon alignment, which is really almost entirely due to my student Lynn, who is brilliant. So, you know, all credit to her. And then if I get to it, I'll talk about this more recent paper on evaluating rodent models. Okay, so LLM alignment, right? So this is just to anchor ourselves to the problem, right? A large language model is presumably a familiar concept, right? But at this moment, the abstraction is going to be a thing which eats some text and spits out a response. Okay, and the structure of this is that you train these things on just some extremely large corpus of found text to get some kind of general purpose language understanding ability, right? Then maybe to make them act as chatbots, you do a little bit of extra formatting, right? You say, okay, like I'm gonna have like a special human assistant key so that it knows to act conversationally. Right, and so you can get a system now which is operating as a given like a prefix of a conversation, it will spit out a response, right? Okay, but then you want a little bit more, right? So you want the response to be high quality or obey some kind of like favorable desiderata, right? So this particular example, which is from the Anthropic helpfulness harmlessness thing, right? In this case, actually, maybe this is totally illegible. But in this case, the human is asking the LLM assistant for advice on how to cheat at poker. Okay, and the default response here, this is like a sample for the model. All of the experiments here are with Pythia 2B, which is like a smallish so-so model. But the default response here is that it says, oh, well, you should get a mirror and hide the mirror such that you can see the other player's cards. Okay, and the goal here in this particular thing is that you want the LLM, maybe you don't, but the goal is to get the LLM to instead chide the user and say, no, you really shouldn't cheat at cards, right? So you want it to somehow give only harmless advice rather than just helping the user do whatever the user wants to do. Okay, and of course there are more obvious examples of undesirable behavior, but I'm not going to put more obvious examples of undesirable behavior on the slide. Okay, so the point is, this is like the default response, and we want to update the parameters of that model in some fashion, such that instead of just like spitting out a response that does this, it spits out a response that has some other set of properties. Yes.
So I guess I'm confused in general, but it also came up yesterday when it comes to alignment. But is the fact that there's some moral issue here something relevant, or is this, and from the person who's talk, the same as saying that you want the output to be, grammatically correct, actually useful, written eloquently?
Yeah, all of those are equivalent. Yeah.
Like, if you have to give me math, okay. So the fact that the fact that it's about cheating in poker is irrelevant.
Yes, yes, totally irrelevant.
Math problem with a correct answer and incorrect answer.
Yeah. Yeah. There is a distinction between like objectively measurable properties, right, and things that are sort of intrinsically more subjective, right? So like whether or not the solution to a math problem is correct, right, is a thing that you can just tell, right, and that does have some kind of like influence downstream. But I think for the moment we can just ignore that. Okay, and so the thing that we're going to talk about in this talk, which was my motivation for starting to look at this, is that when you try to align LLMs to have good, so that the properties are good on some desired attribute, this often induces off-target behavior. Okay, so just regurgitating this, the point of alignment, or like alignment generally means take an existing LLM and update the parameters in some fashion such that the outputs are biased to have desirable properties, right? And that could be helpfulness, factuality, whatever, right? And there are a bunch of methods and formalizations of this, the most famous of which are like RLHF. There's other buzzwords, DPO, IPO, whatever. There are methods for doing this, right? Okay, now as a component of this, it's not merely that you want your model to have some set of good attributes, right? It's that you also want to minimize the drift from the base model, right? So for example, if I want to prevent harmful behavior, a very easy way of doing that is just make the LLM always refuse to answer any question, right? And so the sort of like abstract goal, right, is to get good behavior as much as possible while minimizing like drift or divergence from the base response, the distribution of base responses, right? And the usual formalization of this almost always is that you try to control the KL divergence between the distribution of responses from the updated model and the distribution of responses from the base model that you are aligning.
Distribution of prompts.
Yeah, so
the distribution of prompts is not well defined even.
Yeah, so yes, this is an excellent point. We'll mention this briefly. Yeah, so when you would never do this, I'm sure, but when one writes this down, typically the KL divergence is for a fixed prompt, right? So you want control uniformly over all prompts. But then when you, actually like try to run a method in practice, in fact, you average over some set of like prompts that are used for your training data. And in fact, it's slightly nastier than that, as we will see.
Change the prompt slightly, then suddenly I'm outside your training set.
Yes. Oh, yeah.
So you kind of want to say the prompts don't change much, then my behavior will not change much.
Yes, I completely agree. I really do think there's quite a lot to do in this area with just like a little bit of care. So I think you both are correct in principle, and in practice, I suspect it matters. I'm just going to ignore it for the moment, though. Okay, good. And so the particular issue that we're interested in here is that when I fine-tune my model to try to make it factual or harmless or helpful or whatever, I will often also induce off-target behavior, my attempts to control KL divergence notwithstanding. Right, and so by off-target behavior, the most obvious and famous one is length bias, right? So as you try to make these models more helpful, their responses get much more verbose, right? This is just like a sort of consistent empirical finding, but there are other things like they tend to be extremely sycophantic, right? You know, in a way where it's just kind of unclear why this is happening.
Which direction KL are you? I mean, maybe this. I don't know if we're supposed to get math from this or if that's going to come later.
The math will come later.
Okay.
Yeah. Yeah, we're just this is the qualitative setup.
But I guess even qualitatively, which direction KL are you thinking of? Because that makes a big difference in terms of when you're thinking of what you mean by drift.
The expectation is taken with respect to the updated policy. So the aligned model. But I mean, this is not like a law of nature. This is just the formulation that happens to be used. Okay, good. Okay, so the question that we're interested in here is why does this happen, right? So this is a distribution shift thing, and so the sense when I started working on this is, well, maybe this is a spurious correlation issue. But actually, first let me say the most obvious thing is that the off-target attribute is just secretly actually desirable, right? And this maybe speaks to like the distinction between like mathematical correctness and is this helpful, right? Because ultimately you're evaluating things that are just based on human preferences, right? And so maybe humans actually, you know, surprisingly prefer sort of extremely verbose answers or like really want sycophantic responses from LLMs, right? That's a possibility. Okay. Another possibility, which was, as I said, the original motivation, is that this off-target behavior is ultimately due to some kind of spurious correlation in the data that you are using for your alignment procedure, right? So it might be the case that when you learn the reward model that you're ultimately going to use for alignment, right, just by some virtue of the data collection procedure, it happened to be the case that longer responses were also higher quality, right? And so then when you align the model to this data, right, you know, in a way that should upweight high quality responses, you're inadvertently also upweighting longer responses, right? That's a possibility. Okay, and the third possibility is it's just a bug, right? This isn't anything fundamental to the data that you have or like the nature of the reward model or anything else. It's just you have a particular methodological procedure, right? You're solving an optimization problem and you're not doing a good job of it, right? So by it's just a bug, I mean, if you did a better job on the optimization or you did a better job on the regularization, the issue would go away, okay? And a thing I think of as kind of like a bitter lesson of domain adaptation is that there are a lot of clever and beautiful explanations for spurious correlations and domain shift. And then when I go rather, and try really hard to make things work, what I often find is that if you just try really, really hard to get the baseline to work well, right, then in fact, the sort of like beautiful, elegant explanations are not the right thing. And in fact, it's just a methodological problem. Okay, and so the either happy or disappointing punchline of this talk is going to be that this behavior that we are seeing doesn't appear to have like a nice, like this is a causality problem story. It's mostly just a bug in that we're just not doing the alignment very well. Well, it means someone can solve it. Yeah. Okay, good. So yeah, okay. So the most direct evidence for this would be just solving the problem, doing the alignment well, right? And so let's start off by looking at a variant of that. So this is BonBon alignment, which is Lynn's work. Okay, so okay, I wish I had made this bigger. Okay, so what's being shown in this slide, let's first look at these green and yellow dots, right? What we're gonna do is start with some base model, roughly a 2 billion parameter model, and this helpfulness harmlessness task, right? So we have a wide variety of prompts, right? And the basic scheme is that we generate for each of those prompts 2 responses, right? We then have a ranker that says this response is preferred, right? And there's some alignment procedure, in this case, DPO or IPO, doesn't really matter, right? But which ingests these ranked pairs and tries to upweight the probability of the winner versus the loser, okay? And these procedures come with a hyperparameter, which allows us to adjust basically the KL penalization, right? And so the setup is we have a ranker, which is saying good versus bad, right? And we have a knob, which is controlling KL drift from the base model. Okay, and the thing that is shown here, right, is what you might expect, which is that as we crank down that KL penalty, right, or sorry, for a high KL penalty, we get a relatively low win rate versus the base model, right? So this is just like, does our ranker prefer a sample from the updated model to a sample from the base model, right? But as you allow more and more KL drift, right, you get a higher win rate, right? So I guess there's 2 separate things, right? If you strongly penalize KL, you have a low win rate. If you weakly penalize KL, you have a high win rate, unsurprising, okay? And then the x-axis is showing the average length of the responses, right? So this is a measure of verbosity, right? And so just based on this plot, ignoring these points, right, what you see is sort of a nice monotone pattern where you have more off-target drift, right, but also a higher win rate. Yeah?
So is average length of the response that important in a sense? Like you said, like sycophantic. I mean, it's also like to say something about the nature of the response being somehow
okay, yeah.
less
So
preferred, other than just
okay, so I wish this was in clear resolution, but let's decide that. Okay, so here are 2 examples from an aligned model with a similar win rate. So the question here, the human asks, what is 7 plus 2? Right, okay, so not great resolution. What is 7 plus 2, okay? The reference model, or the base model before any alignment, the response is 7 plus 2 is 9, okay? An aligned model, this thing with whatever, roughly 85% win rate, right? The response is 7 plus 2 is 9, which is the number 7 plus 2. It's a paragraph long response, right? Since the dawn of time, man has wondered what is 7 plus 2, right? Okay, and so it's not, yeah, so the off-target movement here is real off-target movement, right? It's doing something highly undesirable in order to exploit it. Yeah. Yeah, so win rate is, we have a ranker, right, which we are using to fine-tune the models, right? To evaluate the fine-tuned models, what we are going to do is draw a sample from the fine-tuned model or the aligned model and a sample from the base model and rank them, right? Then draw many such samples and compute the average of when the aligned model is preferred to the base model by that ranker.
Ranker is another model?
Yeah, in our case, we're using an off-the-shelf model as the ranker, but you can just consider it a ground truth. Pardon? In this case, it's actually just like literally a model that like eats pairs of prompts and responses and so like spits out a real number. But yeah, ChatGPT would also work.
The weight of the KL requirement, right? The ranker.
So
Without the KL requirement as well. Or
no, the ranker just sees prompt and response, right? And so the knob, the KL knob, is controlling which particular model you arrive at, right? And the ranker just cares, was your prompt response pair good?
Okay. So should we view win rate as saying better aligned?
It just says the ranker prefers the new thing to the old thing.
So why do we care what the
ranker thinks?
Yeah.
Yeah, okay, yeah, good. So in this case, we are treating the ranker as a ground truth entity.
But wouldn't we prefer the old over the new? I mean, like, what information connects the ranker to your preference?
Yeah, so in general, you train a model to reflect human preferences, right? But for our purposes, because we're just trying to understand like what the alignment procedure is, right? We have some ranker given to us by fiat, right? And we are trying to get a model where the ranker prefers responses from the new model to responses from the old model. And the question is, yes. Right. Okay. Yeah. Right. Yes. So the ranker is just defining what alignment means. Yes. Right. That's a much cleaner way of putting that. Okay. And the point is, yeah. Eventually, you see a disconnect.
That's
right?
what I just asked.
Yeah. No. And yes, I should have just said yes. Yes would have been a pithier answer.
One of the verbose answer.
Yeah. Right. We see that there's some misalignment problem here. Too much KL drift. Okay. Good. So the basic the setup, the background for this, the first part is, look, as KL increases or as your KL penalty decreases, you get more off-target behavior and your win rate goes up. Okay. And so you might think you're just doomed, right? But there's a particular interesting observation here, which is you can plot this blue square, which is the procedure where you just draw 8 samples from the base model, rank them, and then return the best one. Right? This is best of n sampling. Okay, and the thing to see here is that this pink square has the best win rate and almost no off-target drift. Okay, so at least for this particular problem, there was some kind of procedure, right? There exists a sampling distribution, right, which really does very, very well on this problem, right? Which is just return the best of 8.
It's no drift in terms of length, but maybe there is a drift in other measures.
Yeah, well, okay, let's push forward. Yeah, okay, good. So yeah, okay, so this is an empirical statement, like folk wisdom maybe, right? Or at least for this particular problem, measured on average length, best of n is achieving a high win rate with relatively minimal off-target drift. Okay, so best of n, again, just generate n samples independently, rank them, return the best one. Okay, and the folk belief, which we just saw a particular instantiation of, is that best of n has excellent performance as a way of generating high quality responses without doing off-target things relative to any kind of explicit alignment scheme that we have to work with. Okay, and so the question for this part of the talk, or the goals for this part of the talk, are understand why this is, right? So in particular, if that's true, right? And then ask, can we use this to improve an alignment scheme and thus resolve the performance versus off-target issue? Yeah.
So, I mean, missing something, but it sounds like for alignment, what you're saying is that all I need is a ranker.
Yeah.
Right. But how do you build a ranker?
So, yeah, okay. So the sort of conventional answer is you get a bunch of humans to rank data, right? You then train a model to mimic the rankings of those humans, right? And then you use the model that you have trained as your ranker.
I mean, I think another answer is to saying, let us look at 2 parts of the problem. One problem is what is alignment. The other part is, once you know what is alignment, what should you do? And he's only addressing the second.
Yes, yeah, correct.
But for me, the moment you know what is alignment, you are done. That's what.
Well, no, because you still have to like make your model output things that are preferred.
No, but by the best of n, once I have the ranker,
yeah. Sorry, right. Okay, so that's a good question, right? So if best of n works well according to folk wisdom, and you have the ranker, why don't you just do best of n always? Yeah. Okay. And so the answer is computation, right? So like drawing these samples is expensive, right? And so the issue is you actually want to like serve these things or do anything with them in practice, right? It's actually not a viable approach to draw 8 responses for every query.
We'll always pick the longest answer, and the best event will drift into longer answers. Because if there is some small probability of getting a long answer,
yeah,
maybe best will always pick this one, and then it will get the same drift.
Let's come back to that. So that I think that's not what's happening, but let's see if we can convince you that that's not what's happening. But yeah, in terms of like if you just had a ranker, yeah, in fact, like basically I agree the best event procedure I think would work, right? And the reason that you can't do it is computational.
Thank you.
Okay, good. So we're just going to establish a little bit of notation, right? So for us, a large language model, which will denote pi, is a kernel that maps prompts to probability distributions over responses, right? And a reward R is a function that takes in a prompt X and a response Y and assigns a real number to it, right? And generally speaking, we're going to be interested in rewards that really are only meaningful relatively, right? And so the meaning is that if response Y1 would be preferred to response Y0, right, then R of X and Y1 is bigger than R of X and Y0. Okay. Okay, and then win rate, which I've already alluded to. You can summarize the overall preference for an aligned model over the base model, right, as the probability that a sample drawn from the aligned model will be preferred to a sample drawn from the base model. Okay, and a particular thing is this is of course not the only way to summarize your preference for reward, right? But this one has the particular advantage that it is invariant to monotone transformations of the reward function, right? And so if your ranker, if your reward model anyways is only reflecting preferences, right? Like the scale is not actually meaningful, right? You would like an evaluation procedure that has the property that it is also invariant to rescaling of the reward. Okay. Good. Okay, so the abstract goal of alignment or informal goal of alignment, right, is to start with the model pi naught that I have in hand and update it to a new model pi r such that samples from pi r have high reward and pi r is close to pi naught, right? Two contradictory goals. Okay, the canonical formulation of this, the standard way of doing this, right, which is implicitly the thing used by RLHF and DPO, is the following thing. You say, okay, I want my aligned model to be the argmin, at least in like some kind of population limit, of this thing where I maximize the expected reward under my updated policy, right, subject to a KL term. I'm sorry, there should be a minus sign here. Like this is an argmax. Argmax minus beta or argmin of negative reward minus whatever, yeah.
At the risk of me handling this conversation, I mean, when you say that this is your goal, is your real goal, do you really care about the aligned model being close to pi naught, or is it just something you use in your procedure because you have finite samples from the finite accesses to the reward during training?
You care about it in the sense that you believe that your base model has a bunch of like general purpose language understanding and capabilities that you would like to preserve.
But that are not captured in the reward?
That are not captured in the reward, yeah. Right, and so like, for example, if I, like maybe my base model is good at mathematical reasoning, right? But I also want to make sure it never says anything offensive or that its responses are like helpful, right? The qualitative goal is to preserve the mathematical reasoning ability, right? While updating on the limited thing that I'm trying to change. Okay. Okay, good. So this is the normal formulation. Yeah, I'm sorry, there's a misplaced minus sign here, but whatever, hopefully it's still clear, right? I'm gonna formalize drift via a KL penalty, right? And a high reward just via the expected reward. Okay, and then I have a hyperparameter beta, right? Which is a knob that I can turn, which controls the reward versus KL trade-off. Okay. Okay, and then immediately, of course, you can generalize this, right? To say, look, instead of going for my expected reward, what I'm going to do is maximize the expectation of some monotone transformation of my reward, right? Because again, there's no like intrinsic scale to these things typically, right? And so an obvious thing that I could do is just apply some monotone transformation. Again, so yeah, this is the canonical thing, and then there are other methods that are based on this idea of applying a particular monotone transformation to some out-of-the-box reward model. Okay, so here's an obvious idea. If the way that we're going to evaluate ultimately is win rate against the base model, maybe what we should do is just directly optimize for win rate against the base model. In on time. Oh, perfect. Okay, right. So we're just gonna do this kale problem, right? Optimizing for win rate against the base model. And again, I'm sorry, there's some minus signs that are just wrong here. Okay, and so the first theorem, right, that we'll want here is that in this optimization problem, it turns out that the win rate against the base model and the Kale divergence can be computed as explicit functions of this parameter beta. Okay, now there's a caveat, which is you need to treat the outputs as continuous, like there's some kind of approximation there, right? But the fact, which is not at all clear, or maybe not at all obvious a priori, right, is that these two quantities that you care about actually do have like analytic forms. And they're not particularly nice analytic forms, right, but they are computable. Okay, and the sketch of the argument is basically recognizing that you can rewrite the win rate as applying the CDF transformation under the base model to the reward itself. Okay, so that's the first trick. The second trick is that when you have these Kale regularized problems, right, there's a known analytic form of the solution, right, which is just an exponential tilting, right? So up to normalizing constant, this is some like classic result. It's just an exponential tilting by that thing, right? And then it turns out that if you use these two tricks together, the integrals that you get out actually become tractable, and you, or maybe not you, but Lin, can solve them, right? And so the point here is just like, there is sort of like some small miracle that occurs that is making this like totally analytically tractable, okay? Yeah, okay, so whatever. This is not important, I just think it's cute. I wish this figure was not here. Okay, so the point is we can explicitly compute win rate and Kale as a function of this hyperparameter beta. Okay, now recall that we were trying to understand is what's going on with the best of n solution, right? Well, we can also explicitly compute the win rate and Kale divergence of the best of n sampling distribution, right, against the base model. Okay, so that's what this is, right? Again, analytically tractable. Okay, and then having computed these two things, right, we have Kale versus win rate. What we can do is plot the best possible policy in teal, plotting the Kale divergence versus win rate, right? So the teal is the Pareto optimal possible solution, right? And we can plot the best of n policy, right? And what you see here is that the best of n policy is essentially identical to the Pareto optimal policy, right? And so this plot is just showing the absolute, or sorry, the percentage point gain in win rate between the optimal policy and the best of n policy. And this is largest at best of 2, right, at which it is 1 percentage point, right? And so these things are essentially identical, right? Yeah?
We're gonna want to lie on one point on this graph, right? Like we want to, or I assume the final user is going to want to stop at some point where
Yeah. So it's a knob you have to choose, right? So the more Kale you have, like the more Kale budget you have, the higher your win rate will be, right? And what we were trying to figure out is for a fixed Kale budget, what's the best possible win rate you can achieve.
But how do I pick between the, like, I assume there is some practical, or I think there might be some practical heuristic here that you might want to pick up on, or is it like?
Yeah, I mean, you, I guess, ultimately send it out to a bunch of users and see if they like the thing that you have better or not. Yeah, so I mean, it's choosing a hyperparameter, right? There isn't like a nice recipe, but the point is you just want, like, for any given level of KL budget, you would at least like to do the best you possibly can on the win rate at that KL budget. Okay, and the point is the best of N policy achieves that. Okay. Good. Okay, so this sort of answers the question of like what's going on with best of N. It really is optimal, right? And maybe this convinces you that yeah, in fact, fine. Maybe if you went to high enough N, you would eventually see something going wrong. But or you know, you still believe that. But the dominating effect here is that you just are getting a much more efficient trade-off. Okay, so this doesn't solve the computational problem. Right, this tells us that best of N is the best possible thing that we can do, right? But we still can't actually do it, right? And so a thing that we might like to do is now say, okay, well, based on this, what we want to do is align a large language model to its, so that the policy that we get by updating is equal to the best of N sampling distribution of the base model, right? So we know the best of N sampling distribution is the best possible thing. The cost is linear in the number of samples. Yeah, and it's expensive to draw the samples. I don't know, N equal, I mean, the cost goes up linearly with N, right? So.
But you think the advantages will just be only for large N's?
No, even for small N, but like if you double the cost, that's already prohibitive. N equal 2 is too expensive.
Can I push on that question?
Yeah.
So even if N is equal to is expensive, how expensive? Would it be something that a human would notice?
It would be something that the data center, which is serving the model, would notice. Like you need to build a second power plant.
I mean, you'll notice because subscription fee would be $40 instead of $20.
Okay.
Yes.
So I think this is probably like a bit off topic, but one of the really strong motivating arguments for you here is computational cost. Like, have you thought about like what if you use a smaller model, but then do like best of N versus like one larger model? Like, what's the trade-off between like the underlying accuracy versus?
Let me completely punt on that question in the interest of getting to the end of the first half of my slides. But it's a good question. It's a good question. I'm just not going to answer it. Okay, good. So look, we want to align the LLM to its own best of N policy. Okay, how could we do that? Well, here's the most obvious possible idea. Just draw a bunch of samples, rank them, pick the best of N one, and then just use supervised fine-tuning or equivalently maximum likelihood estimation on those samples, right? So just the same way that you train the LLM in the first place, take the good samples, run gradient descent to update in that fashion. Okay, so this obviously works in theory, right? The problem is the convergence rate is extremely slow, right? So you would need like a truly vast number of training examples to get anywhere. It's computationally prohibitive. Okay, a slightly more clever idea is based on the following observation, which is that, some typo there, but essentially the log likelihood ratio of the best of N sample and the worst of N sample under the best of N distribution and the base distribution can be computed analytically. Yeah, okay, 3 minutes, that's fine. Okay, so the point is there's an analytic expression for this thing, right? And so what we might do is say, okay, my objective function rather should be, let me find the model pi, right? Such that the likelihood ratio or the log likelihood ratio, right, between pi on the best of N and worst of N samples, right, versus the log likelihood ratio under the base model on those same two samples is equal to the difference that it would have been under the best of N policy. right? So the point is just this quantity is analytically computable for the thing that we are targeting, right? And so our objective function is just learn a thing that matches the known analytic solution. Okay. Okay. And the problem with this is that works, but it only controls the ratio of these probabilities, right? And this is actually a generic problem with these contrastive methods, right? And so what happens empirically when you run something like this is that the probability assigned to your losing solution goes down, which was what you want, but the probability assigned to your winning solution also goes down, right? It's just everything in your training data becomes less likely under the aligned model, right? Because all you're controlling is the ratio, not the absolute probability. Okay, and so the BonBon alignment idea is just use both. Okay, just take a sum of these two objectives, right? You'll get the speed up from this guy, but this thing cares not just about ratios, it controls like the absolute probability assignment, and so you largely solve the problem. Okay, and a particular thing worth noting here is that in contrast to every other thing, like every other existing method, it's too strong, most other existing methods, right, have some kind of explicit knob controlling the trade-off between KL and win rate, right? What we're doing here is controlling this implicitly by the choice of n used for the training data, right? And so in particular, this is going to sidestep some optimization problems related to like how well can you measure the KL divergence. Okay, so obligatory machine learning graph, machine learning talk slide, right? So here's a method where we train a bunch of models and show that the thing that we propose does in fact work better, right? So this is the KL versus win rate Pareto curve as you increase n from 2 to 8, right? Okay, and you see that this is in fact a little bit better than what you could do with the baseline methods, right, in this KL thing, although of course still much worse than actual just best of n. I mean, maybe not of course, but yeah, it is still much worse than actual best of n. Here's the same plot, but where instead of measuring the KL divergence, we explicitly measure some off-target attribute, in this case, the average length of responses. And what you should see here is that the average response length using the BonBon method at a high win rate is much, much less, right? So indeed, we're genuinely getting way less of this like this verbosity problem. Okay, I think I'll just do this slide and then stop. Okay, yeah, so just one more thing that I want to point out before I wrap up is that actually on these trained models, the correlation between measured KL divergence and response length is not very strong, right? And so, so you really see that, like, recall that these guys have the best win rate, right? The interesting thing is that the thing that you are explicitly measuring, or the thing that you are explicitly enforcing, right, either because we are measuring it incorrectly, right, or because it's just not the right quantity, is not actually controlling this like extremely off-target behavior, right? This example where we saw the answer to 7 + 2 is like a paragraph of word vomit, right? That is not actually showing up as bad behavior under the measured KL, right? And so it does suggest that there's like another gap there to fix, which I don't fully understand. Okay, and so I will stop here. Yeah.
I'm wondering, isn't mixture of experts the implementation of best of them?
I feel like maybe we should take that off. So the question was, is mixture of experts in some sense an implementation of best of n? And my instinct is no, but it's not a very strong instinct. And so I'd be interested to chat about it, I guess. Yeah.
Okay. Let's take it offline to the break. Okay. Thank you.